Hi, good evening, ladies and germs from the Measurement 4 practicals for Vaal University of Technology. The idea of today's experiment here is to show you guys how to do EMI, EMC measurements using the practical setup that we have demonstrated in the lab. Our equipment, very basic. We have a spectrum analyzer, I've got a power supply, I've got a radio transmitter and receiver because we're going to be using this to confirm our transmissions. And over here, I've got a homemade radio transmitter with a folded dipole antenna. The idea of this setup is the transmitter is going to create a radio signal for us. That signal is unfiltered because of a very poor design on the PC board. And the results will be harmonics that we will witness on the instrument. Let's start with the circuit itself. The circuit is a very basic circuit. It has an audio input. I am driving it with 12 volt power, the red and the black crocodile clips. And it is crystal oscillator with a small adjustment here. Pre-stage, second stage, multiplying the frequency from the crystal, going to a final radio stage, and that is then connected via coaxial cable to the dipole. The dipole is set up for the frequency which should be around 100 megahertz. The reason for my 100 megahertz is this transmitter the idea behind it was to use it as a small transmitter for communal transmissions. Once this thing is on, we should be able to hear something. So what I've got here is my radio. It is set up very close to the region of frequencies. And because we are in the Faraday cage, we do not expect to hear really anything useful at this stage. Once I switch on the power supply, immediately a couple of things happens. Number one, my radio transmitter is transmitting, and I see it on the scale on the radio receiver here that indicates that at this range of frequencies there are some stuff. So if I scan through the frequency, I can easily see where is it peaking. And at this stage it's peaking roughly at more or less 100.4, 100.5 megahertz, which is what we are expecting, isn't it? If I touch that circuit, I should be able to hear finger. Now if I had it connected to a sound system and a microphone, that audio would have been modulated on FM and we would have received it here on the radio receiver. I would like to draw your attention now to the spectrum analyzer. The spectrum analyzer is a wonderful device. It detects and measures for me across a range of frequencies all the radioactivity that it can measure. What I've done with the setup is very simply an antenna, and this instrument I'm somewhere using a very standard rubber ducky, nothing funny, and if I disconnect the antenna immediately, nothing is on the screen. If I connect it back, then I start seeing radio signals, and that's what I'm looking for. I'm looking to see where this device is transmitting. Now, if you are following the method in the practical guide, then you will find that first instruction was connect the equipment. Second part of the instruction is to transmit and to determine the main transmit frequency. To do that on the spectrum analyzer, very simple. I've got function control, I've got markers, I've got my settings control over here, and the idea then is very simple to control my measurement from here. So that we go to frequency, we say center frequency 100.5, so I put in 100 megahertz, and now in the middle of my screen I have a peak here. And if I ask for the instrument to show me the peak value at 100 megahertz, there I have my first transmitted frequency. I need to prove to you that it is this one. So I'm switching off the power supply. to the transmitter, and the transmitter stops transmitting as expected. Also, on the radio receiver, the noise has returned. The white noise, the same noise floor that we are seeing on the instrument. I switch it on, and I tune it up, and I pick it. I will find nicely quiet, full quieting, radio term. We will talk about it in another experiment, but my signal corresponds to where I'm receiving it. Very nice. So 100 megahertz, 100.0, that's where my transmitter is sitting. If I touch the transmitter, you'll notice, no, that is very hot. And you also see that I can affect the way that my circuit is working. So normally we don't touch the electronics because obviously you do affect the radio transmitter. Back to my measurement. We now know the main transmission frequency, 100 megahertz, and it's sitting at an amplitude of minus 30 dBm. Take a note of that value, minus 30 dBm. Then we're going to change my frequency range. I'm going to go and see this little frequency that's standing up here. What is that? So my range says from 0 to 200 megahertz is what I'm looking at. So I want to see what's happening at this point here. So let's increase my stop frequency for the screen, and I make it say 250 megahertz. Now I'm spanning up to 250 megahertz, and I can see very clearly there is a second harmonic sitting here. So, question, what is the peak? I still have my first one, 100 megahertz, and if I have the next peak, then I can see it is at 199.5 megahertz, and at minus 42, or make it minus 43. It jumps a bit, but that's normal. Minus 43 dBm. So from 0 dBm is down to minus 43 dBm for this setup. Keep in mind, the antenna of the spectrum analyzer is not connected directly to the output of the transmitter. We are taking a radio, an airborne signal, and we are doing the measurement on the spectrum analyzer. So, next question. Are there another peak that we can witness? So I'm going to back frequency, change my stop frequency. In this case, I want to move 100 megahertz further, 350 megahertz. And if I do this, then I can actually see a third harmonic coming up. Going back to peak control, the next peak, then this one, 299.6 megahertz. At minus 48.4 dBm. And to confirm the middle one, 199.5 at minus 47 dBm. The amplitude's more or less the same, but they're definitely dominant into this measurement. So there we have 1, 2, 3 signals that is given by the same source. So which means the transmitter is transmitting, but it's generating harmonics. So I switch it off just to prove that it is definitely my transmitter that we are receiving. If I increase the span of the frequency range, 350 was it now, I make it 450 megahertz. There is yet another peak coming up here, a little finger. And that indicates to me that there must be another harmonic sitting there. If I change my markers, I can run the little block, and we will find that this one, a little bit of fine tuning, there it is, just under 400 megahertz, 399.4, 399.4, amplitude minus 51 dBm. So there is a decline in amplitude. Remember, this is minus, so the bigger the value, the smaller the amplitude. And it's dBms. Remember about dBms? It's with reference to 1 millivolt power that we are using. So there we go. 1, 2, 3 harmonics and the main signal sitting this side still very predominant. So the question is, can we find another harmonic? Well, let's try it. Frequency, stop frequency. We were stopping at 450, so now we go 550 megahertz. And within the noise, yeah, there is something. There is something. Peak. Let's just find our marker. It is running through the screen across the noise floor, and if we are lucky, that's a nice one. And if I keep on turning, then you will notice a little box sitting here on the finger there, just over 500 megahertz. It's about there, 503.6 megahertz. Amplitude 50.05, I would say, is a reasonable value to use. 1, 2, 3, 4 harmonics that is present in this transmission. Now, why is it a bad thing? The thing is, at 200 megahertz, we are interfering with television service. At 300 megahertz, we are interfering with some military services. At 400, you are interfering with vehicle security alarm frequencies. At 500, you are up at the UHF side of television service. So you don't want these harmonics to be present on frequencies other than the one that you are transmitting. For that reason, a filter is used. And one of the questions are, what type of filter should be recommended? A high pass, a band pass, or a low pass? That I leave for you to figure out. So, do we have another peak that we can look at? At this stage, the experiment works very well. So let's change our stop frequency. We did stop at 550. Let's go to 750. I'm taking a big jump, megahertz. And you will notice 1, 2, 3, 4. And then something very small here and something very small there. You think it's relevant? Of course it's relevant, but it's not that much. So what we do is, when we look at standards, and the standards of SABS, and the standards of the IEEE, and these type of organizations who are looking at standards, we decide, is that signal strong enough to cause interference? If so, why? And if not, why would that be either? So that we can actually decide whether it's within limits of use or not. So to recap, our main transmit frequency at full strength, all the harmonics, there's a relation in the frequencies, and you can work it out based on our values that we have now measured. So this one is, with relation to that one, seems to be double. This one is another one there, so this is times 2, times 3, times 4, times 5, times 6, and 7, and so on. So if it was predominantly strong, we would like it not to be present there at all. And with that, I turn your attention to the practical guide, finish the answers, hand it in, and thank you very much.